All right, so FRQ number 4. Again, if I have any mistakes or corrections, I will put it in a pinned comment. So please check that before you point out the other things I'm probably going to get wrong here. Okay, online game. Players move through a virtual world collecting geodes, a type of hollow rock. When broken open, these geodes contain different crystals of different colors that are useful in the game. Red crystal is the most useful crystal in the game. The color of the crystal is independent. Probability geode contains a red crystal is 0.08. Sarah, player, will collect and open geodes until a red crystal is found. Okay, that's a geometric distribution because you're not doing a fixed number of trials. They're independent trials, and there's only two outcomes. Either you get a red crystal or you don't get a red crystal, right? So we want to know the mean and number of until a red crystal is found. Show your work. It's not a lot of work to show. The mean for a geometric distribution is 1 over p, where p is the successes, probability of success. So probability of success is 0.08. So this is going to be 1 over 0.08. And that's going to be 12.5. 12.5, let's see, what do we call it? Mean number of geodes. Geodes. I like to always just put geode. Now, I don't know the show your work part. Is that sufficient? You might want to say this is, you might want to say the distribution itself. They're sometimes picky about this. It's geometric, where the p is equal to 0.8, because 0.08. That is p is the probability of success, and success in this case is getting a red geode. Or red crystal. Okay, I think that's sufficient. I don't think you need to show much more than that. I don't know, maybe someone who knows the intricacies of the weird AP Statistics grading can probably tell you, but that's probably all I would put in. I'll look at the scoring rubric in August when it comes out and see if they wanted something more than that. Calculate the standard deviation of the distribution number of geodes Sarah will open. Well, standard deviation is just a formula. You can either, I don't think, I'm going to not derive it, so I'm just literally going to just say, well, it's still geometric. And let me pull up the formula sheet so you can kind of see where the formula is. All right, so I pulled it up here, and so you can see here was the mean, right? And then here's the standard deviation. So the sigma x is just going to be this formula, square root of 1 minus p. Oh, oops. We just write the formula. We already indicated it's geometric, so I don't think you need to do that. 1 minus 0.8 over 0.8, and that is going to be the standard deviation, right? So square root of 0.2 divided by 0.8. And that's going to be 0.5590. The units of that is also number of geodes. Standard deviation has the number of units. So, you know, I would put the units if you remember to do that. That's the nice thing about standard deviation. It does have the same units as the mean. Another player, Conrad, decides to play the game, will stop opening geodes after finding a red crystal when 4 geodes have been opened, whichever comes first. Oh, so it's kind of interesting. It's whichever comes first. So it's not either. It's kind of not really a binomial, not really geometric. It's just going to be a kind of thing we have to generate. Let y be the number of geodes Conrad will open. The table shows partially completed probability distribution. So So how does this work? If he opens a red geode right away, he's done. Otherwise, he's going to keep going, right? And so the second one means that in this case, if he got to this point, how did they get this number? They got this number by saying, oh, well, he didn't open it the first time. The first one wasn't, right? It wasn't a red crystal. And then the second one was a red crystal. So when they multiplied those two, and let's just confirm that that's what they did. That gives you 0.0736. Okay, and then these are the probability that the number of geodes Conrad will open. So then the third one here is going to be, well, the first two, which were independent, is this is me not getting a red crystal, and then I get a red crystal, right? So this would be 0.92 times 0.92 times 0.08, and that's going to be 0.0677, okay? Now, 4 is basically, he's going to stop here. So for number 4, it doesn't matter if he gets a red crystal or not. It's just going to be whatever the remaining probability is. So, like, you just do 1 minus all of these because the total sum has to equal 1. Because the 4 doesn't have to be a red geodes. It just means, like, he's going to stop. He's going to open this one regardless. and it doesn't matter, and that probability is going to be 1 minus 0.008 minus 0.0736 minus 0.0677. So we're going to do 1 minus 0.08 minus 0.0736 minus this number, and I get this to be 0.7787. Okay, so that is the table there. Calculate the probability that y equals... Oh, I'm sorry. I didn't even read the problem. Okay, probability y equals 3. I had to show your work. So I did it up here, right? But this is going to be 92 times 92 times 0.08, and that's going to be 0.0677. And I would show a little bit more than that. I would not just show that. I would say, I would write these as probability events, like if they want you to show your work. So I would say the probability that the first is not red times the probability, so the probability that the third is red is equal to probably the first is not red times the probability that the second is not red, given that the first was not red, and then times the probability that the third is red, because that's when he would stop, given that the first and second are not red. So that's like in probability notation, right? That's that probability of A and B is the probability of A given B times the probability of B, right? So it's kind of like this. That's where these probabilities kind of come into play. Okay, probability y equals 4, and show your work here is that the total probability, or the probability of y equals 1 plus the probability that y equals 2 plus the probability, because he's never going to open more than 4, plus the probability of y equals 4 is equal to 1. And so then this is 0.08 plus 0.0736 plus 0.0677 plus the probability of y equals 4 is equal to 1, and then you can say the probability of y equals 4 is going to be 0.7787, like that. Oh, circle your answer there, like that. Okay. Consider the table and the results from part B. Calculate the mean of the distribution number of geodes. Conrad will open and show your work. So how do we do expected value, right? So this expected value of y is you're just going to do the count times the probability. 1 times 0.08 plus 2 times 0.0736 plus 3 times 0.0677 plus 4 times 0.7787, right? So we're just going to do that, and that is how we calculate the expected value. So I will just bring that down there for the notes, just so you can kind of see that. And let's do that calculation real quick on our calculator. That times 4 plus, and don't use the rounded values. I truncated these to 4 digits, but they're actually a little bit longer, right? So don't use the rounded values. Round at the end. 1 times 0.08, and I get that's 0.7418 geodes. Okay, so, that doesn't look right. Oh, oops. Yep, no. It's got to be close to 4. That's what I was. I made a typo in my calculator real quick. I should have just showed it on the calculator so you guys can see it. Sorry, I should have. Plus 4 times this probability. It's going to be 3. Sorry about that. Sorry if I panicked you. 3.398 geodes. Should be close to 4 because the high probability that it's like he's going to get for 4. Interpret the mean of the distribution number of geodes Conrad will open, which was calculated in part C. So when you do mean of a distribution is if Conrad repeatedly does this, repeatedly does this by counting the number of geodes he opens. So he repeatedly did this. On average, he will have opened 3.398 geodes per trial. Okay, repeatedly does this trial. I'll call it a trial. Where he kind of repeated, I don't know a better word for it. Repeatedly does this experiment where he just kind of like opens geodes. Right? If he does it over and over and over and over and over and over, then the average times is gonna be 3.39 for each trial that he does it. That's gonna be the average number of geodes. That's the interpretation of the mean distribution. You always want to say like it's the average number if you do it for large number of times, right?